Okay, this is sample problem 9.1. Determine the shape of SO3 and ICl4 minus. Okay, so here's the strategy you want to do. Let's start with problem A. The first step is to draw the Lewis structure. When we're doing shapes of molecules, molecular geometries, we draw the Lewis structure first. So S O O O SO3. Then we do our counting of valence electrons. Sulfur is in group 6A, so it has 6 valence electrons. Oxygen is also in 6A. There are 3 oxygens, so that's 24. We've already used 6, so we're down to 18. We distribute those 18 electrons equally on the surrounding atoms, if possible, in the form of lone pairs. This is all Chapter 8 material. Next thing we do is we look at the central atom. If the central atom is electron deficient, doesn't have enough electrons, as sulfur does, sulfur only has 6 here, we pick one of the oxygen atoms, a lone pair from that atom, and push it over to form a second bond, in this case a double bond, an additional bond, in this case a double bond, to the central atom. Of course, it doesn't matter which oxygen we pick. We could have picked either of the 3 oxygens. That's an issue of resonance. For shapes of molecules, that doesn't really matter. So now what we do is we identify what I would call the formula of this compound. So sometimes we can do it this way. We'll do AX, and the A represents the central atom, so sulfur would be the A. The X represents the surrounding atom. How many are there? How many surrounding oxygens? There's 3. Next, we identify whether there are any lone pairs on the central atom. If there are lone pairs on the central atom, we would write in, let's say if there was 1 lone pair, we would write in E. If there were 2 lone pairs, we would write E2, and so forth. But there aren't any lone pairs, right? On the sulfur, we're only talking about the central atom. Okay, so it's just AX3. And then we can use a little logic to this. If we have 3 electron domains, 1, 2, 3, an electron domain is 1 or more bonds to a surrounding atom, or a lone pair. So the sulfur has 3 electron domains that it's attached to. Doesn't matter whether it's a single, double, or triple bond. They're still 1 domain. So it has 3. If the sulfur atom has 3 electron domains, we would expect those domains to be located equidistant from one another, or equiangular. So the oxygen atoms should be equidistant from each other. And geometrically, that would require an angle, just like a triangle, of 120 degrees. Okay? And the name of that is trigonal planar. Okay? And there you go. So there's the SO3 trigonal planar. Now, let's take a look at the second one. The second one is iodine, the iodine tetrachloride ion, ICl4 minus. Turns out this is going to be an example of an expanded octet for the central iodine. So the iodine is bonded to 4 chlorine atoms. We don't know whether they're single, double, or triple bonds. Turns out they're going to be single bonds. let's do our valence electron counting. Iodine is in group 7A, so there are 7 valence electrons. Chlorine is also in group 7A, so it also has 7. So that's 35. We've already used 8. Oh, sorry, I forgot one more. It's ICl4 minus. We've got to add one more electron. So it's 36 electrons, not 35. Okay, I almost made a mistake there. So it's 36 minus 8 is 28 electrons remaining. We've already used 8 for these single bonds. So we distribute them around the surrounding atoms to get to octet for each of those. So how many are we going to use to do that? If we have 4 surrounding atoms and each is going to get 3 pairs, how many electrons is that? Well, 6, 12, 18, 24. We still have 4 left. So we're going to have an example of an expanded octet. 1, 2, 3, 4. Remember, we never get the surrounding atoms above 8. It's only the central atom. If you do a formal charge calculation, you'll find the formal charge of iodine is -1. Okay? Unusual, but there's our structure. Of course, we use bracket notation for the Lewis structure. Okay? Now we ask ourselves, what do we have? We have a central atom. We have 4 surrounding atoms. And we have 2 lone pairs on the central atom. So that would be our formula. Okay? That particular arrangement of electrons, or electron groups, electron domains, I'm sorry, I was losing track of the word, electron domains, is that essentially you have 6 electron domains. On 4 of those domains is a chlorine atom, and then on the other 2 are the lone pairs. So in a sense, it's an octahedral. But the arrangement of atoms are what we're concerned with, not the arrangement of electron domains. The arrangement of atoms are actually flat. It's a plane in the shape of a square. So we call it square planar. And all the angles are 90 degrees. Okay, so that's called square planar. So let me show you. I'm going to come down to an additional page here. Your textbook has a couple of tables that you can use to kind of figure this stuff out. But in general, it follows the same this idea. If you have a central atom and you have 2 surrounding atoms, and there's no lone pairs on the central atom, that's going to be linear. And your angle is going to be 180 degrees. If you have 3 surrounding atoms and no lone pairs, that's trigonal planar. And the angle is 120. If you have 4 surrounding atoms and no lone pairs, that's called tetrahedral. And the angles are all 109.5. If you have 5 surrounding atoms and no lone pairs, this is called trigonal bipyramid. Okay? And the angles here are, there's 2 angles, 120 and 180. And then AB6, 6 surrounding atoms. This is called octahedral. And these are all equidistant at 90 degrees. So those are the cases where you have no lone pairs. Now what happens is, when you have lone pairs, these angles change. So let me show you just real quick what these structures look. Well, actually, I'll show you them real quick. A is at the center, and then B's are away from 180 degrees, just like that. That's 180. Trigonal planar, like this, 120. Tetrahedral, a little harder to draw. This is 3-dimensional. Oops. The 3-dimensional ones are harder to draw. So it goes like this. And then coming out of the plane of your drawing, and then going into the plane of your drawing. 109.5. Okay, that's your tetrahedral. So there's the first three. The next one is the trigonal bipyramid. So I'll do that one over here. Notice I'm using B in the notation instead of X. Some books use X, some use B. Your textbook uses a B. Okay, so you essentially have a little triangle here in the center. And that's the 120 right there. These are all 120. But then you also have this angle from here all the way down to here, and that's 180. So that's your trigonal bipyramid. Last one's octahedral. We can draw it like this. 90 degrees. Each of those angles is 90 degrees. Okay? So there's your those ones. So the SO3 falls into the trigonal planar. This one right here. But we also have some other arrangements that have lone pairs on the central atom. And so I'm going to show you a couple of those, not all of them, but at least a couple. So let's try AB2, E2. Remember what that means? That means you have two lone pairs on the central atom. So for this one, A is in the center. You've got really 4 pairs of electrons. 2 of them are surrounding atoms. There's your AB2, but 2 of them are lone pair. So what happens is the angle here is close to 109.5, just like the tetrahedral, like we drew over here, where you have 4 electron domains. We also have 4 electron domains here. But what happens is, because the structure, the shape of a molecule is based on only the atoms, not the lone pairs, that angle there is a little bit under 109.5. It's about 104.5 degrees, although it could be larger. We call this bent. Okay, so that's your bent arrangement, AB2, E2. If you have AB3, E, so 1 lone pair but 3 surrounding atoms, all I'm going to do here is I'm just going to replace one of the lone pairs with a surrounding atom, AB3. So this is just like a tetrahedral as well, so it's a little under 109.5 degrees. But with 3 surrounding atoms and only 1 lone pair, it's a little higher. It's about 107 degrees. And this one is called trigonal pyramidal. Looks like a little pyramid. Okay. The next one I want to show you, I'm not going to go through all of them that are in your table, but the next one I want to show you is what's called the T-shape. I'm sorry, not the T-shape. Let's do the linear. So if you have AB2, E3, okay, with the AB2, E3, what happens is the central atom is here. There are 2 surrounding atoms, and then you get, around the equator, you get 3 lone pairs. So if you actually look at the arrangement of the atoms, it's just in a straight line. So this one's linear, 180 degrees. Okay. Let's take a look at one more. The next one is the case where you have 4 surrounding atoms and 2 lone pairs. Okay, that's interesting, right? Essentially, think of them as connection points. There's up to 6 connection points to the central atom. That's what's observed. So if we have 4 surrounding atoms, actually, let me do it this way. It's a little bit better visually if you do it this way. If we put the 4 surrounding atoms like so, and put the 2 lone pairs like this, you get a little square, right? So that's a square planar. That's the one we saw with ICl4 minus. And the angles are all 90 degrees. Okay? So there's a bunch of these. I mean, it's not that many, really, you think about it. If you're thinking about all the small molecules, the number we're talking about is really around 11 different shapes. It's not that many. The most common ones are these ones, these first 5 up here, AB2 all the way through AB6, or AX2 all the way through AX6. And then here's a few more. There's the bent, the trigonal pyramidal, and the linear, and the square planar. There are a couple of others. There's what's called the square pyramidal. Okay, so that would be AB5E, one lone pair but 5 surrounding atoms. Okay, so that's one possibility. There's another one called the T-shape. That one's kind of cool. So that's the case where you have 3 surrounding atoms and 2 lone pairs. Okay, 3 surrounding atoms, 2, not 4, but 3. And then another one is called the seesaw shaped. Fun names, right? So this is the case where you have 4 surrounding atoms and 1 lone pair. Okay, so the number of lone pairs on the central atom affects the shapes of these molecules. So the square pyramidal looks something like this. The lone pair is coming off like this. Okay. The T shape, well, looks like a T, essentially. The T shape looks like this. You got A in the center. Make a little more room here. And then your B comes out like this. And then you got a couple lone pairs here and here. So there's 2, that's your T shape. Looks like a T, right? And then what does the seesaw look like? Well, the seesaw looks something like this. You got the central atom. You have 2 surroundings, just like a linear, like in a straight line, and then going into the board and coming out of the board. Looks something like that. Okay, so there's your seesaw shape. There's your T shape. And then there's your square pyramidal. And that's pretty much all of them. Okay, there you go.